And welcome to to Dispersing and Milling. My name is John Kowalski. I'm part of the marketing team here at Gardner, and welcome to our latest edition of our web seminar series. Today we have Mr. Andy Stummer presenting. He's our business line manager and all-knowing on things dispersing and milling. He'll be presenting. We are also recording this, and immediately following, you'll receive the link in the email. Feel free to watch it later, send it to colleagues, however you like. Also, if you have any questions at all, please log them in the chat box located in the bottom right-hand corner of your screen. Time permitting, we'll get to them. If we run out of time, we'll follow up with you directly next week sometime to make sure all your questions are answered. So with that, let me turn things over. Andy, it's all yours, sir.
Thank you, John. Welcome everybody to today's seminar on dispersing and milling. It's an intro seminar.
Can't hear you, Andy.
Hello?
Okay, we'll see here. Some technical issues. Hold on.
Hello? 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 Hello?
Yes, Andy, we can hear you.
Can you hear me?
You're good to go, Andy.
Okay, thank you. I apologize for the snafu. Thanks everybody for joining us today. This is an intro on dispersing and milling, and we'll dive right in. So basically giving you guys an overview, just a little feedback on the company. Then we dive right into the dispersion process. We're going to cover the pre-dispersing as well as the milling part, which is actually two parts. And then we're going to do an overview on some lab and production equipment and just talk a little bit about different QC capabilities and also the lab capabilities that we offer here in Wallingford, Connecticut at Big USA, and also at VMA in Germany. And you can already see on this slide right here, VMA makes instruments, dispersers, and milling system from laboratory all the way up pilot and manufacturing scale. So that slide really shows it very nicely, all the different types of equipment that we offer. So the company, VMA, was actually founded about 50 years ago by this really nice couple up on top right, by Herman and Elke Getzmann. Herman actually used to be a co-founder of Anton Paar, probably a company some of you are familiar with. And when he sold out, he took the funds and he started VMA. He wanted to own his own dispersing and milling company. So the VMA Getzmann company was founded in 1972 in Germany, about 30 miles east of Cologne. So that's right in the center of Germany. Big has had the exclusive distribution rights for VMA products for North America since 1988. The company is now run by the two children, by Martin and Christian Getzmann. So it's still in family hands, and they have roughly about 100 employees today. They're all over the world, and basically they have high-end milling systems, dissolvers, as well as different types of attachments like the rotor stator, and we will cover those as well. And there's a picture of the very first DISPERMAT that you can see that was built in 1973. There's actually still some customers that are still using the original DISPERMAT design today. So it speaks a lot about the technology and the quality of the motors. And if any of you ever used a DISPERMAT, you would realize how quiet they are, and they're just really awesome pieces of equipment. So here is a picture of the company. This middle piece right here And that part actually was added on right before COVID. So they have additional laboratory capabilities as well as new manufacturing capabilities. They have about 8 people right now in the design center, just designing the different types of DISPERMATs. And Herman, who founded the company, still comes into the company about twice a week, just to ensure that they still follow his design philosophy and make sure that everything runs smoothly. 40% of everything that VMA manufactures or builds is basically custom. So there's a lot of different requirements on different end-use markets that require specialty machinery, and VMA Getzman can really accommodate those different specifications. And then we have some really high-end laboratory capabilities in Germany at VMA or at Big USA in Wallingford, Connecticut, where we added a lab about 3 years ago with a lot of different dispersing and milling capabilities to show to our customers. So just a couple intro information here, a couple points. So mainly the equipment is obviously used to disperse pigment, but there's also different new end-use markets where the machines are used. For example, battery slurries, food industry, cosmetics. So there's many other applications, but mainly we differentiate here in the pigment world between 4 different pigment classes. So we have obviously the organic pigments, inorganics, functional pigments, and then the special effect pigments, which we have to treat a little bit differently because we don't want to destroy the effect pigments. So any type of shear that's too much could actually destroy or damage these aluminum flakes, especially effect pigments, and that would give us really poor results. So at the end of the day, what we want to do is when we properly disperse our pigment, we really want to see improved gloss, just overall better appearance. Obviously, our color strength is much improved, and cleanliness of shade, just among some of the attributes that we are able to improve by dispersing the material better. So therefore, we want to achieve better wetting. Main goal is to really break up these invisible forces. They're also called Van der Waals forces. They act almost like magnetic forces that keep these primary particles, pigment particles, bound together. And we want to basically break them up. So the idea is to really reduce these larger agglomerates and return them back to the primary particle size. That will give us obviously improved color strength and again better appearance, gloss. Our efficiency is improved because customers will need less pigment because we are better dispersing them. That will also help us save money on our raw material costs, gives us better product consistency, helps us with the formulation improvement, and good dispersing will give us also much better particle size distribution. And if we go into production, we should also see really good upscale results by having good dispersion results. So here are some issues that we face if we improperly disperse our pigments. So obviously we want to have really good and stable color, flocculation of pigments, sagging, leveling, settling. Some of these are common issues. Obviously gloss is an important one, and separation. So these are just some of the things we want to avoid. So therefore we want to just have really good dispersing results with the equipment. So here are some critical properties. So obviously, pigments, we want to have really strong color fastness. They will help us fading over time. So stability, brightness, the brighter the color, usually the better the color. We also look at, particle size reduction. So the rule of thumb is the smaller the pigment, I have improved transparency and better color. And obviously, again, we're saving money because we need to use less pigment in our formulation. And another caveat here is usually we want to have lower viscosity. That will also help us with processing the material and will lead us to improve particle size distribution. So it's really important to keep in mind that we're really only reducing the particle size. We are not trying to destroy our pigment particles. Some people think, because we are employing a shear, a blade or a cow's blade, the teeth will actually chop these pigments up. And that's not really what's happening there. We're really just trying to break up these binding forces and basically turn these larger pigment clusters, these agglomerates, into aggregates. And then finally turning the aggregates into primary particles when we do the milling, which we'll talk about as well. And so the shear forces are really responsible for that separation and breakup of these binding forces. And then at the end, we also need to keep in mind should be using some additives to keep all these particles then in a suspended state. So it's just a slide showing you different types of pigments out there and what their particle size is. So it's an interesting slide I thought I'd throw in there. And so here you can see these larger clusters of pigment particles, these building blocks, we call them agglomerates. And then the smaller building blocks there are called the aggregates. So we really want to break up these binding forces with the cow's blade to go from the agglomerate down to the aggregate level, and then from the aggregate level down to the primary particle level. This is where we actually will do our secondary dispersing, or fine grinding, or milling as it's called. So we actually have two steps: the pre-dispersion, go from the agglomerate down to aggregate, and fine dispersion, aggregate down to the primary particle size. So this is a good slide showing you kind of what that looks like. So with the cow's blade, we're actually wetting, breaking up these binding forces from the aggregates, from the agglomerates down to the aggregates, and then we move over to a milling system, either horizontal bead mill or a basket mill, or you could use a vertical a pot mill, as they're called. We call it APS system. We'll talk about that. And then finally, we want to stabilize these pigments so they stay in a suspended state. Here is a really good slide that kind of details at what point we want to move over to a bead mill. So a dissolver is really good for all your larger clusters, your agglomerates, large particles, 100 microns or smaller. And then we use that dissolver with the shear to really break up these large particles. And once you reach roughly the range of 10 to 20 microns, that's when we no longer have enough shear force with the cow's blade. We really need to move to a bead mill. And that will help us then to go to much, much smaller particle size, all the way down to sub 50 nanometers with the right type of media. This should not be a problem. But basically, you can see right there is a threshold, and 10 microns is really the limit of how small you can get with the dissolver. And you shouldn't go higher with the bead mill with large particle size because the problem is then you need to switch out the beads. And if your particles are too big, there's always clogging of the screen or the dynamic gap. So it's always good to first, and important to first, use a dissolver to break these large particles and then go to the milling systems. So we actually have a number of solutions, obviously, for pre-dispersing. But what is really critical here is the tip speed. So it's not always just the RPMs. The RPMs are just one part of the formula. But we need to actually look at how fast is our blade spinning. And depending on the blade diameter, if I keep the RPMs constant, that tip speed will always change. So you have to always remember that in order to have optimization of a pre-dispersion process, we want to be anywhere between 18 to 25 meters per second. And for the fine grinding or milling, it's a little bit slower. We want to be anywhere between 10 to 16 meters per second. And so obviously we use dissolvers for the pre-dispersion process. And then for the fine dispersion process, we have different types of milling systems. We'll cover those as well. So for the pre-dispersion, what is really important to remember is always the geometric considerations. So the blade, obviously blade type, but also the ratio to the container. And you can see here, we have that also online, and you'll find that table in our catalog. It really shows it really well at what point should you switch to a larger blade. So on the bottom here is your container volumes, and then here you can see the type of blade diameter. So there is not one blade that's perfect for all the different volumes. Obviously, you have a range of blade diameters that would fit for each different type of vessel size, depending on the viscosity. So it's really important. And if you're not going to have the right blade ratio, then you will not have very good dispersing properties, and you will not see a donut effect, which is the optical cue to see what's actually happening during the dispersion process. So we'll go into that in a few slides. But this is the formula you should write down, and that's actually how you calculate the tip speed. Some of our higher end machines will actually display that on the control panel, and some of the standard machines you'll actually have to calculate it. That's the formula. And if you want to figure out meters per second, then all you do is divide that whole formula by 60, and the diameter would be expressed in meters. So if it's 40 millimeters, it would be 0.04. That 0.04 meters is 40 millimeters. And then what you would do is divide the whole equation by 60, and that would give you the meters per second. Obviously, you can also figure that out in feet per minute if that's what you prefer, but that would be the equation to calculate the tip speed. And that is actually one of the most important values that we are looking at when we are dialing in our equipment for optimization of the pre-dispersion process. The donut effect, I don't know, some of you may have heard of it. This is actually really a term that is used to describe what we see when we look inside of the container, the vessel with the product, if it's optimized. So that is actually right here, a really beautiful looking donut. And that's what we ideally want to see. Over here, you can see the breakup of the binding forces. So if I optimize my tip speed, I have the right viscosity. We're looking here between 2,000 to 5,000 centipoise. That's really optimum to get a good donut. You can also get a donut, obviously, with high viscosities, but usually for most coatings, we see really good results in that 2,000 to 5,000 centipoise viscosity range. If you're dealing with really low viscosity, sometimes it's more difficult to get a donut because the donut would collapse immediately when it gets formed because the viscosity is so low. And here you can see the breakup of these binding forces is really happening at the edges of the blade. And actually on this graph right here, I would have added that same on the bottom because we are actually also achieving the particle breakup of the binding forces on the bottom of our blade as well. So here is an example of a really good optimized dissolver batch with a nice looking donut. We have 21 meters per second of tip speed, 850 watts of energy input, and basically that gives us a real good looking donut, and it's optimized dissolver batch. In this case, we have the same tip speed, but only 320 watts of energy. So we're not putting in a lot of energy. It means our viscosity is kind of low of the material. So in order to pump that up, we need to improve our viscosity, to put more energy into the mill base. That would also give us a better looking donut. And then in this case, we're putting 900 watts of energy in, 21 meters per second, also not really optimized. And basically, we don't have a donut at all. So the donut is important. It's the visual cue to tell us what is really going on with our dispersing process. So here are the key differences. So we have obviously dissolver. We're going to have only a blade, the cowls blade or the impeller blade, or the dispersing blade, as some people refer to. We only can input a limited amount of energy, therefore limited amount of shear force, and it's only the first step in the dispersing process. So it's really only to de-agglomerate and turn these larger particles down to the aggregate level. And for primary particles, we would need to do the bead milling. And it is the necessary step for any dispersion process. And if you omit the bead milling and you only want to work with the dissolver, you're physical or appearance and color properties will be impacted by it. Your color will not be as bright or beautiful as if you were also using the milling systems. So because there we can put way more energy into our mill base because we are also using media. It's for further deagglomeration. As again, with the right bead mill setup, we can go down to sub 100 nanometers, no problem. And that's where we really get down to the primary particle size. And by doing so, we will have a much better color strength, better transparency, gloss is heavily improved, and also we get a much better particle size distribution as a result. So in order for us to optimize our dispersing process and results, so we need to always observe the duration of our pre-dispersion. The rule of thumb there is between 15 to about 30 minutes. We should have properly pre-dispersed our mill base. The donut effect, again, is the visual cue we want to see. Tape speed, again, 18 to 25 meters per second for the pre-dispersion. Again, remember to keep the blade diameter in the right ratio to our container vessel. And then obviously the right type of blade, as there are many on the market, and depending what viscosity you have, you're working with, you would pick the right blade. Then again, the amount of product in my container, usually there, the rule of thumb is about 50%. Up to 70%, we don't want to go higher or we're going to spill the product. So about 50 to 70% there is the rule of thumb. Obviously, our pigment and filler concentration plays a big part in it. We want to keep the temperature as low as possible. Obviously, when you're dispersing or milling, you're going to add a lot of energy and put a lot of heat into the mill base, and therefore we like to use some cooling to really keep the temperature as low as we can. And then at the end, obviously, we want to use additives to really improve our results for wetting and dispersing. And obviously, we don't want the pigments to flocculate back together. And then the bead mill would then be the second step. So here are some of the differences. Basically, with the bead mill, I can add a lot more energy. I can deagglomerate all the way down to nanometer range. And that's really the breakdown of the primary particles, which you will not be achieving with just a dissolver. And again, the color and transparency and gloss is heavily improved. So what is actually happening here in the bead mill is that as these media or as the beads collide towards and drift towards each other at very high velocities, our pigment particles actually get sheared, and that what creates that breakup of that binding forces. So that's what's really happening inside of our bead mill. So the kinetic energy is one of the most important parts we need to look at, and that always comes up when I'm making a bead selection. So some people prefer glass beads because they're less expensive, but their kinetic energy is a lot lower than stainless steel beads or ceramic beads. And we want to stick with ceramic and not steel beads because the problem with stainless steel or metal is that because of the milling action and just the beads getting thrown around the milling chamber, it's going to wear. And that would cause the material then sometimes to shift color. So if you're trying to produce a light or a white product and you're using metal beads, then it could happen that the mill base would turn gray. And we want to avoid it. Therefore, we highly recommend that you would use ceramic media. So also, this is a great slide showing you the influence of the bead weight. So if I have small beads, it's almost like I have a small hammer and I need to have many blows before I could drive the nail into my board. That's kind of the same thing in the milling process. And if I have a larger bead, it's like using a larger hammer, one blow and the nail is already in the board. So you always want to look at the kinetic energy influence for the milling process. And this is a good slide here showing just the difference between the zirconium oxide, serum stabilized bead. Just look at the specific gravity, the weight there, 6.1 versus glass, just a 2.5. So there is already a big difference there. And then also look at the hardness. The zirconium is much harder than glass. The issue with glass is they wear unevenly, the glass beads, and then they break up, and then you end up with shards in your mill base that you have to filter out. We've seen that, and that's also not advisable. So always stick with higher grade beads. They cost a little bit more, but they're really worth the money. Okay, so that slide is great because it shows you kind of where actually during the milling process that breakup of these binding forces happens. And it's actually right in the corners right here. So it's not in the middle of when the beads crush each other. It's really like they're getting like squeezed out. It's like you're in the water and you're trying to catch that rubber duck in a bathtub, and it always wants to go away from you. And that kind of is the same principle. So as you push your hands together and the duck tries to move away, that shear is actually what's happening inside of the bead mill. So as the beads collide together, that force is actually pushing the pigment particles away from the beads, and that's the shear force that's responsible for that separation. So kind of giving you an idea what actually is happening inside of the bead mill. So here are some critical parameters, obviously, that we need to always watch out for when we are milling in the second step of the dispersion process. So we always have to have that right particle size in our bead mill, because we don't want to have larger particles because they tend to clog up the screen or a dynamic gap as we have in our horizontal mills. Again, the bead size plays a very important role, the weight of the beads, the bead volume. There is always tables for each of the different milling systems that will describe exactly what percentage of beads you need to put in to the system to have the optimized bead loading. The shape of the beads is also very important. So we always recommend that you screen the beads not after every trial, but once every week or 2 weeks, depending on how often you use those beads, to ensure that you get rid of the fines and the broken up bead particles, if there are any, because that would lead you to uneven results. And if you try to be repeatable in your trials or your process, you always want to have good bead consistency. And again, this is always very important. Write that down. The tape speed of your rotor or your milling disc should be between 10 to 16 meters per second. So it's quite a bit slower than what we see in the pre-dispersion process. Temperature, even in milling, it's even more critical than in the pre-dispersion process. Why? Because I'm adding a lot more energy into my mill base when I'm using media. So the product temperature control becomes even more important. So double wall container, or with the milling, a horizontal mill, we have chilled milling chambers, as well as milling or supply containers that are double walled. So that is really, really important. The number of passes, how often do I circulate through my milling chamber? Do I go pass through, or do I go in circulation mode? So that also plays a role into my milling results. How long am I milling for? And how long will actually my mill base stay inside of the milling chamber? So that depends on my pump or my rotor speed. So all these things have to be optimized to really achieve the best milling results. And then obviously the viscosity of my mill base. We want to have a viscosity that's 2,000 to 5,000 centipoise. Some products obviously higher. That's not that critical, but if in milling, if my viscosity is too low, like water, then it's going to be more difficult to put in enough energy. So higher viscosity, if you can make that happen in the formulation process, will usually allow you to put in more energy during the milling process, which should give you better milling results. Okay, so here is a great example. Just want to show you our DISPERMAT solution, the modularity, that if you have just a benchtop dissolver, that's the DISPERMAT AE, that's kind of our flagship model, but that principle holds true to all the different systems. we can have a number of different attachments that will all fit onto the same machine. So you have a rotor stator, you have a APS system, you have a wall scraping system, you also have a basket mill system, and you can add a vacuum system as an attachment to the standard dissolver. So you're up on top here, you can see that clamping ring right there. That is actually what we call the quick change system with the DL shaft. That's a bayonet style change system. So that allows you to go from dissolver very quickly to any of these different attachments and turn a disperser or dissolver into a bead mill, which is very cool because you only need one instrument for the lab instead of multiple instruments. It's very quick. You can make a changeover in less than 1 minute. And now you're turning the dissolver into a milling system. It's really, really cool. So don't want to go through and spend a lot of time on all the different models, but that's kind of an entry level system. Personally, I'm not a big fan of DLC. The reason is you have to manually lift the motor up and down. There is no up and down. So that lever right there will allow you to just lift up the motor. If you want to oscillate the product, and that's not really convenient because you always have to manually move it up and down. So it's better to use something like the CV, where that's all done electronically. So you have an up and down button that allows you to move that motor up and down. With this system, it's also capable of measuring temperature. You have a timer function. It also gives you a torque value, the percentage of torque. That's kind of an indirect measurement of your viscosity of the mill base. So that's a really nice machine. It also comes with the safety features. So we have the container clamping system that wheel right there ensures that the container is tightened and always centered perfectly underneath the dissolver blade. There is a sensor back here that measures the pressure, and if the pressure sensor does not read that it's tightened enough, the machine will show you on the display and it will not run. We have also the ability to set thresholds for what we call the working area. So we have an upper and a lower threshold that we can set with that slider on this side and one on the back. And that allows us to lock in that working area to ensure that the dissolver will operate in that range. But if somebody were to lift up the machine while it's running, the dissolver would automatically shut off once it crosses that threshold. And on the bottom, once it reaches the bottom point, it can't go any lower. Therefore, the blade would never hit the bottom of the container. So that's really important. And with the CV technology, you can set these parameters. The next system up is the CN technology. Has a little bit more capability. That safety area, what I just talked about, that working area, you have now an additional two buttons on the display. Instead of having that slider on the side of the column, you do that electronically on the display. The great thing with the CN line is that it's also expandable all the way up to pilot scale. So within the same product family, we have much larger machines that can go up to about 150 liters of product. So we have customers that basically say, I like to have a lab scale, but I want to also be able to produce at a pilot scale within the same product family. So the CN is really a good machine for it. And also that modularity that I showed you earlier holds true to all of our DISPERMATs. So also on this machine, you would be able to put in on the different attachments that I showed you. We have the AE model, which is our premium line. That machine is also available from lab scale all the way up to pilot. And it comes with the C technology package, which is our most advanced quality control and R&D package. It has very good upscale capabilities. It allows you to send data over to a computer to store data by batch name or by product ID. And then at a later point, you can recall it, and the machine would automatically use the exact same processing parameters that you're able to replicate the trials exactly the same way every single time. And if you want to go upscale, the data here is really helpful because it allows you to seamlessly go from lab scale all the way up to production scale. So we also offer production capability, and this is a really, really good software package that we offer if customers want to track data, upscale, and have the most control. You can run this machine not only with a certain speed setting, but you can also dial in a certain amount of energy you want to put in so that the machine will automatically adjust the speed depending on your viscosity levels. So we call that feature constant power. That allows you then to more precisely calculate actual manufacturing costs because you know exactly how much energy you would be using to disperse a certain amount of material in a certain amount of time. Again, that modularity is available just like on all the other models, and it comes with a software package that allows you to then see the entire dispersing process in real time on a graphical interface. So each of these critical values like speed, torque, time, heat, or temperature, they would, or energy input in watts, they would all be displayed in a graph, and you could see a trend line for each of these critical values. Even if you're not in front of the system, it can be in your office. So that's very, very powerful. So here is an example of the basket mill. Just showing you that's one of the attachments. So basically our basket mills have the ability to also cool themselves. So we have cooling rods. So there is cooling in and cooling out. Cooling fluid in, cooling fluid out, so they are double walled. So we're actually cooling the entire milling basket, which is really important. We have a screen on the bottom. Some of our competitors have a screen on the side. We believe that that's where we actually really need to cool the product, so that's why we have the entire mill closed, and we have the screen on the bottom. Below the screen, we actually have a cowls blade, and that is really important. That cowls blade helps us to drive the mill base out through the mill and suck it out of the mill through the screen right there. And then on top, we have a pumping and steering wheel that's patented that allows us to then draw the mill base back into the container. So you would see that you have a very, very effective and good circulation of your mill base in and out of the basket mill in the container. So that's the design. It's patented. It's really effective. And we have a lot of people or customers that actually are moving away from horizontal milling and move over to the basket milling because it's just a lot easier to use. I wouldn't say necessarily always faster, but the cleaning is much better because you don't have as many wear parts. If you have ever worked with a horizontal mill, it will take you a long time to take the mill apart to clean it. There's a lot of smaller parts in a horizontal mill, and also more wear parts. Whereas here, I don't really have a lot of wear parts except my milling disc and my screen. That's pretty much it. I don't have any bearings or no seals that are in here. So it's a lot easier for cleaning. So just to give you an example, a basket mill in the lab, I can clean rough cleaning 5 to 10 minutes and a solid cleaning in about 25 to 30 minutes. If I would have to do the same thing on a horizontal mill or competitor horizontal mill, that would take probably 1 to 2 or maybe even 3 hours, depending on what color I'm running. So there is a lot of advantages by going with a basket mill. And we also offer basket mill systems for production scale now as well, all on the same modularity. So if you're trying to enhance your production capability, you're able now to actually disperse one machine and then just put a basket mill onto the same machine. Or we have also combination systems that already include the basket mill, so you don't have to switch containers around. So there's a lot of advantages to going with a system like that, even for manufacturing. That's just a great example, a slide here, graph that shows you the rotation of the flow of the mill base through our basket mill, so that cowls blade on the bottom really does a great job of drawing out the mill base and then pushing it up around the container side, and then that pumping and steering wheel that we have on top that actually draws it back in really nicely. The only, I would say, a disadvantage to a basket mill is if the viscosity of my material is too high and I don't have good flow, then it's a little bit more difficult to to get the product put through the mill and back out. So this is really good for lower viscosities to mid-range viscosities. I mean, we have customers that use it up to 100,000 centipoise. That's okay as long as the material is still flowing. So that is the most important thing to watch for here. Also, one of the thresholds is even though there is a nano kit available, you're going to have somewhat of a limitation in terms of particle size. On a basket mill, we can go down to roughly 500 to 600 nanometers. If we want to go smaller, then we really need to look at a horizontal mill for really, really small particles. That's an example of a production scale basket mill. So up here, we actually have a bead filling port, and then you can see the cooling rod is right here. It's also a stabilizer rod. And then on the back here, we have the cooling fluid out. And then behind here, there's a third rod that actually measures the temperature. So the great thing is we're actually able to measure the exact temperature of the mill base inside of the basket mill, where we have the highest energy input and where we have also where we see the highest temperature rise during the process. So here are just some features. So the basket mill system is a batch system. It's very simple design. Again, with the cooling, we're able to really maintain a good temperature. With the quick change system, the DL shaft allows us to move seamlessly from a dissolver over to a basket mill. Very easy handling. And with the nano kit, I can go down to 0.2 millimeters beads. This is one of the larger systems for manufacturing. And we can also offer a vacuum system for operation. If we want to remove any air, then would help us transfer the product from one vessel to another much faster. And also our milling efficiency would be improved because these air bubbles would act almost like it's like tiny air mattresses. They would be like buffers. And by removing those, I should have a more efficient milling process. And from our lab scale with the C technology going to production, we have a very, very good upscale scaling results, almost 1-to-1. Here's an example of a 2 manufacturing grade DISPERMATs at a pigment disperser company. Pigment manufacturing company, dispersion company. So here we have a system. It's called the DisperMat TM, and that is the combination. So this actually has a dissolver. The disc is back here. They're not installed yet, and the basket mill already integrated. So the customer does his pre-dispersion in the container, and then when he's ready to do the milling, the fine grinding, all he does is pushes a button on the control panel, and then the basket gets lowered, and now the whole thing turns into a milling system. That's really awesome for them because instead of having multiple pieces of large equipment, they just have one machine that does everything from pre-dispersing to milling. It's really cool. So they bought 2 of them. They run 7 days a week, and they have extremely good milling performance. That's the DisperMat TM. And we have the APS system. The APS system is not really for production scale. That's perfect for the lab. It's basically a pot mill. Our system there was designed to basically give you a very quick milling results, but also being able to really efficiently move product from one container to another post-milling. So in our container on top, we actually have a screen on the bottom with a drain plug and a lid that goes over it. So I would pre-disperse first. When I'm ready to do milling, I just replace my cowl's blade and put a milling disc on my dissolver. Then I would add my beads, would push down my lid, and then I mill in the same container as I did my pre-dispersing. When I'm finished with my milling process, I would actually remove the drain plug on the bottom of my container, hook up an air hose into my outlet on my lid or inlet, and then use air pressure to purge my mill base out of that container into my catch container below. So the only thing that would be left in my top container when I'm done with my milling process would actually be my beads. So that is actually really efficient. I can use very small beads, less than 0.1 millimeters. So I'm able to go down super, super small in particle size, very narrow particle size distribution. The only drawback is that I cannot really go to production scale because there is no production scale equipment available in this kind of design. So it's really perfect for lab applications, somebody who wants to do a lot of quick colors, small volumes, and very fast cleaning. So that would be the best solution for those type of applications. So you can see here 30 milliliters to 7 milliliter container sizes, so really flexible for the lab. So lab dissolvers come with the safety features. They can go up to 20,000 RPMs. Again, that modularity. We have explosion-proof models for the premium models like the C technology ones, like you can see, like the AE. They allow you to use the software. And then again, we go from lab pilot all the way to manufacturing with our equipment. So the dispersers then can function obviously as a standard disperser with the cowls blade or a media mill, also as an emulsifier by using a rotor stator attachment, or we can just simply use it as a mixing tool by putting on a propeller blade or a butterfly blade to properly homogenize our materials. So we also have obviously the QC control. We can set that up on the machine itself on the C technology. That's just two examples of what these control boards look like. With the C control package on top here, you can see your speed, RPM. Below that, we have the amount of energy we are putting in the mill base in watts. Your torque value, which is the viscosity measurement. The actual tip speed, which is that critical value we talked about. Temperature and a timer function. And so a little bit more simple on the standard M technology, just RPM, amps, and also the temperature readout. We have customers, they want to program their own interface. We have that capability with Siemens. For example, somebody might want to install a scale and have that same capability on the display and tie the disperser into the milling system, the scale system. So that would be a solution that we can also offer for our production scale equipment. Right now, unfortunately, lead time about 1 year on the Siemens controller. This is just an example of the QC software. We can program all the different parameters, like the working area, the height of the impeller in the container, the amount of energy or speed we're putting in, temperature. We can program cutoff values. That's great if I don't want the temperature to exceed a certain point. I can say, or I can teach the machine that once it reaches that point to either reduce the speed, shut off completely, or reduce the amount of energy or torque that it's putting into my mill base. So I have a number of ways on how I can design my process for my trial or my manufacturing environment. And I can do all that on that interface right here. We have net power calibration. That's just a feature that allows you to set the machine to an absolute 0 point so that no machine input, like the mechanical power it needs to operate itself without product, is calculated in, for example, a torque value or the energy input when it's displayed. So we call that a net power calibration. So that is just the Windows 7 that you would see on your computer. It's a little dated, but we are working actually on Windows 10 right now. So that's going to be released very soon. And that's going to be a whole new user interface. But that's basically how you would be able to control or see the data that DISPERMAT is, the processing parameters on your computer. Okay. Just our lab in Germany, where we can do a lot of trials. We have all different DISPERMATs, vacuum systems, really, really awesome applications lab with customers that go there to visit, especially if they want to go upscale and look at the production capabilities to do factory acceptance testing and so on. We will do that there. And then we also have a high-end laboratory at VMA, at Big USA. We added a lot of new capability to that lab as well. Just two of the latest pieces of equipment that are in there is the new AE6 with the C control panel, as well as the new horizontal SL mill. Really beautiful design, very, very good machine for somebody that needs to go down to really small particle size. Perfect for also for battery slurry development. It's a big player in that arena and can be used for many, many different types of applications. So the lab in Wallingford gives us a lot of capabilities. The one that I want to point out, number one, we can demonstrate the customer the capabilities of the equipment, but we can also bring in our expertise from the additive side and really help customers to improve formulations, answer technical questions with regards to formulations, use different types of additives, and really use that know-how that they offer. So we want to come to you with a complete package, not only as somebody who sells you a piece of equipment and then lets you run with it. We are there for you to offer you also the whole package. And we are the only company that really does that, because we have our Big USA sister facility, and that's where that dispersion lab is located. So we welcome everybody that is interested in visiting us up there, or if you want to come in to do a trial, we can also use it as a showroom to show you how the equipment actually works without running your material, if that's something you want to do. Or we can also offer you the location as a seminar location if you want to train your employees on milling techniques or technology. We can also set something up for you. And that's it for today. Hope you enjoyed the presentation and got some better insight into the dispersing and milling process. Thanks, everybody.
Yeah, thank you, Andy. Great information as always. We might have time for one question. If anyone wants to add one to the chat, we have a little bit of time. If not, like I said, you'll get a link with the recording immediately following this presentation. It's automated from marketing. If you have a question, you can just hit reply. It'll come to me or my colleague, and we'll get it Andy or our technical people in your region. Oh, you're welcome. Just got another comment in here. So also, here's a question from Dustin here. If you cannot increase velocity before milling, it's not an option. What are the best options to still get proper deglomeration?
I'm sorry, viscosity or
yeah,
velocity?
Viscosity. He cannot increase viscosity before milling.
So we would need to know what is the viscosity he's working with, first of all, and then there's a number of things we can do. We can add more energy, maybe increasing the speed, adding more beads would help sometimes. For just among some example, a longer milling time. Usually if my viscosity is lower, meaning less energy, means more milling time. So that's kind of like how we would approach it.
Okay. Does that help, Dustin? You're welcome. You're welcome. Yeah, if you'd like us to follow up directly with you and talk about this more, we'd be happy to. See you, Dale. Thanks for joining us. So look forward to the next round of web seminars by Bit Gardner, both this format, which is our 60 minutes, and we also have a monthly office hours, which is a more condensed presentation, usually 20, 25 minutes, followed by a longer Q&A. So stay tuned for invites on that. Thank you for joining us, and we look forward to seeing you on future web seminars. Thank you, and have a great rest of your day.
Thanks, everybody, for joining.